Welcome, my name is Moreira and thank you for watching my presentation. Evaluation and numerical modeling of logical approach for az31b-f magnesium alloy under multiaxial fatigue. In this presentation, I will follow this order: introduction, theoretical background. On theoretical background, I will talk about a widely used constitutive model, the Armstrong-Federic plasticity model, and a new phenomenological model called I-post-strain to describe the cyclic elastic plastic behavior of magnesium alloys. Later, I will present the numerical implementation, the experimental tests, the results, and finally draw the main conclusions. The reduction of pollution and fuel consumption is an important goal to the transportation industry. Magnesium alloys have been attractive to use in structural components, mainly due to their high strength and low density. The weight reduction of vehicles has a strong effect on the reduction of greenhouse gas emissions and also on the fuel consumption. Magnesium alloys show peculiar plastic deformation mechanisms under cyclic loads. Thus, the magnesium alloy cyclic behavior is quite different from the one found in steels or even in aluminum alloys. One of these differences is the symmetry found in magnesium alloys in the hardening behavior and in the yield stress at compression and in tension. At present state of the art, it is not possible to accurately estimate the stress-strain relation of magnesium alloys using the available constitutive plasticity models. The commercial finite element package softwares do not have intrinsic cyclic plasticity models to modulate such type of materials. For ductile materials, they assume that yield stress in tension and compression are equal in absolute value for the same strain amplitude, which is true for steels but not for magnesium alloys. In this sense, a new phenomenological approach, called I-post-strain, has been developed to capture the symmetric behavior of magnesium alloys. One way to account with the unusual cyclic behavior of magnesium alloys with the commercial finite element packages is to implement an external subroutine that can update the material cycle response. Therefore, the main goal of this work is to implement the phenomenological I-post-strain approach on an external subroutine to run on ABAC standard. There are two types of cyclic plasticity models: the constitutive and the phenomenological models. The constitutive models are based on solid mechanics approach. On the other hand, the phenomenological models are mainly based on the experiments. For magnesium alloys, the constitutive plasticity models have strong limitations. In general, constitutive plasticity models have three main parts to follow the material response under plastic deformations: the yield function, the flow rule, and the hardening rule. Armstrong-Federic model is a nonlinear kinematic model. On ABAC library, the von Mises yield function is given by F, where S is the deviatoric stress, alpha is the back stress, and K is the yield stress. The kinematic hardening is governed through the back stress tensor. C and gamma are material parameters that can be obtained by an appropriate material calibration procedure. This new phenomenological approach, called I-post-strain, is a kind of mapping of the material behavior of magnesium alloy based on experimental results. This model is able to accurately describe the cyclic elastic plastic behavior of magnesium alloys. From the experiments, it was found that az31b-f magnesium alloy stress loop can be approximated with a very good accuracy using a third-degree polynomial function for any value of total strain. In order to obtain these functions, it is considered 6 specific points on a stress loop as shown in figure 1. For the tension branch, the polynomial function is obtained using the experimental data at points 4, 5, 6, and 1. On the same way, the polynomial function for a compression branch is obtained using the experimental data at points 4, 3, 2, and 1. This procedure is repeated for shear stress loop. Any point of the stress loop between 1 and 4 is obtained by a cubic interpolation. Under tension torsion loading condition, it is obtained two stress loops, one for the axial loading component and another for the shear one. Therefore, I obtain two different stress loops which are dependent of each other. This dependence is captured by the strain-amplitude ratio given by the shear strain to axial strain ratio. In this study, it was defined the strain level as a square root of the sum of the total axial and shear strain. Each one of the 6 points corresponds to a function that has into account the strain-amplitude ratio and strain level. Therefore, the P1 and P4 functions estimate the stresses for the maximal total strains. The P2 and P5 functions estimate the plastic strain increments inherent to the maximal total strains, and the P3 and P6 functions estimate the back stresses. Under multiaxial loading conditions, these P functions have the following shape. To implement the hyperstrain model in Abaqus, the following tasks are essential. First, define the material parameters. Second, calculate the tangent-stiffered matrix. And third, update the material parameters and the tangent-stiffered matrix based on different stress status. The first step is to define the material parameters. These two material parameters can be easily obtained by the third-degree polynomial function used on analytic hyperstrain approach for the axial and shear component. These material parameters aims to map the asymmetric material response of magnesium alloys. The E parameter for the axial component corresponds to elastic plastic models. If the material is in the elastic domain, it expresses the Young models. On the other hand, if the material is in the plastic domain, it expresses the tangent models. On the same way, the G is another material parameter and corresponds to the shear elastic plastic models. It expresses the elastic shear models in the elastic domain and the elastic plastic shear models in plasticity. The second step is to define the tangent-stiffered matrix in Abaqus subroutine. The two material parameters are used to calculate the elastic plastic matrix. However, to define the elastic plastic matrix, some considerations was done. Poisson ratio was set equal to 0.35. It was constant in elasticity and plasticity. Between two consecutive points, it was considered that the material parameters E and G vary linearly. The phenomenological hypostrain model implemented in Abaqus subroutine to capture the stabilized stress loops for uniaxial and biaxial loadings. The third step is to update the material parameters and the tangent-stiffered matrix based on different stress status. The material parameters E and G were updated in 10 different stress status during a cycle loading, according to the triangular displaced amplitude, except for the non-proportional loadings that were used the sine wave amplitude updated in 12 different stress status. All the tests were performed considering the ESTM standard instructions and using a servo-hydraulic machine. The az31b-f magnesium alloy specimens used on the experiments were machined along the extrusion direction. The following tests were performed: pure axial loading, pure shear loading, proportional loading with strain amplitude ratio for the condition of 30 degree, 45 degree, and 60 degree, and also non-proportional loading with strain amplitude ratio for the condition of 45 degree and a phase shift of 90 degree. These figures present the results of the multiaxial proportional loading with strain amplitude ratio for the condition of 30 degree. In these figures, the black dashed line represents the experimental results, the red line the hypostrain analytical model, the blue dashed pointed line the hypostrain approach implemented in Ambux-Rubertin, and the green dashed line the Armstrong-Frederick model. It can be seen that the phenomenological hypostrain approach was successfully implemented in Ambux-Rubertin. The analytical and the finite element implementation of the hypostrain approach follow very well the axial and the shear experimental hysteresis loops. For the axial component of the proportional loadings, the Armstrong-Frederick model gives a good estimative for the maximum stress limit in tension, however, fails to capture the maximum stress limit in compression. This is more evident for the strain level of 1%. This is because the magnesium hardening in compression is lower than in tension. For the shear component, the Armstrong-Frederick model estimates much lower maximum stress limits than the experimental tests. For the strain level of 1%, the hypostrain approach gives a conservative deviation on the compression hardening behavior. The main advantage of the hypostrain model comparatively with the Armstrong-Frederick model is the possibility to simulate the strain amplitude ratio effect in the elastic plastic behavior, so it can accurately capture the plastic deformation mechanisms that occur in the cyclic response of magnesium alloys during multiaxial proportional loadings. Regarding the non-proportional loadings, the Armstrong-Frederick model also fails to follow the experimental results. For the strain level of 0.83%, the hypostrain model results are close to the experiments. However, for the 1.14% of strain level, the model cannot follow with absolute accuracy the shear mechanical behavior, despite estimating the plastic strains, the back stresses, and the stresses at the maximum total shear strain with very good accuracy. The phenomenological hypostrain elastic plastic approach was successfully implemented in Ambux-Rubertin. The Armstrong-Frederick model showed poor estimations, especially for high strain amplitudes. In multiaxial proportional loadings with strain amplitude ratio for the condition of 30 degree, the hypostrain model followed with very good accuracy the stress strain curves. For 90 degree out of phase loading with the strain level of 1.14%, the hypostrain model fails to capture the shear behavior. Thank you for your attention.